potential value to science emerged. George Harlow of the American Museum of Natural History is investigating what makes carbonado so special.
Carbonado is a conundrum because it doesn't have the characteristics that we associate with diamonds that formed in the mantle on Earth.
Diamonds originating in Earth's mantle form under immense pressure and high temperature, so they're compact and dense. Not black diamonds. Using a microscope, scientists find they're riddled with holes.
It's got a lot of void space in it. Now, deep within the Earth, the void would have to be filled with something. Well, the something ain't there.
Normal diamonds contain very little void space. As they form deep in the Earth, they're crushed into a single crystal. Carbonado seems to form differently. Unlike normal diamonds, it's composed not of one crystal, but millions, all linked together. Scientists conclude carbonado formed not under high pressure like normal diamonds, but low pressure. But just where does carbonado come from? Once again, research leads to the last gasp of a dying red giant.
The current theory for the origin and genesis of carbonado is that the small diamonds formed in supernova explosions.
Haggerty believes the vacuum of space explains carbonado's unique structure.
The diamonds were hot, one diamond bashing into the other, and they finally became glued to form a larger diamond.
During its explosive formation, specks of mineral dust are also trapped, making the large diamond appear black. The diamonds are then transported to Earth by a meteorite.
When the meteorite hit, it showered diamonds, so this must have been a truly amazing sight, with carbonado diamonds being liberated from the meteorite on impact.
It's not just the large size of space diamonds that fascinates scientists. Carbonado has another advantage over regular diamonds. Its multi-crystal structure makes it not only larger, but tougher. It's almost impossible to cut. Not so a natural diamond. Although it's one of the hardest materials known, it has weaknesses. It might seem surprising that conventional diamonds aren't naturally flawless. But in New York's jewelry district, it's this inbuilt weakness of natural diamond that is exploited by gem cutters. Their work illustrates just why single crystal diamonds are of little use as a template for scientists hoping to create an impervious superdiamond. In the cutting room, it's marked up with a pen so the cutter has a guide. Further computer analysis identifies the natural flaws in the rock and calculates the best place to split it. These days, lasers have replaced hammers and chisels to shape diamonds, but the actual cutting still relies on finding the diamond's natural cleavage plane. A natural single crystal diamond will split cleanly where its chemical bonds are weakest. By following this cleavage plane, a gem cutter can split the stone perfectly. For scientists, this weakness in single crystal diamonds is a fatal flaw. Diamonds that might fracture aren't durable enough for high-tech use. The key to making a tough super diamond lies in replicating Carbonado's multi-crystal structure. Their theory of how Carbonado forms in the vacuum of space yields another breakthrough, a whole new way to make diamonds.
The space diamonds have now taught us that in fact we don't need pressure at all. This can be done in a vacuum.
Carbonado sets the stage for a new kind of super diamond, one tougher and larger than ever, that can be made into multi-crystal shapes not found in nature. The key is using low pressure to simulate the vacuum of space. This process is called chemical vapor deposition, CVD for short. It begins with a tiny diamond seed, sealed inside a vacuum chamber slightly below atmospheric pressure. The chamber is heated to almost 2000 degrees Celsius. Then methane, a carbon-bearing gas, is pumped in. Then hydrogen. The gases are bombarded with microwaves, which agitates them, forcing the hydrogen and methane molecules to collide. This process releases a cloud of carbon atoms that settle on the seed, and gradually the diamond grows. This was the seed they started with. 24 hours later, it has doubled in size. At the US Naval Research Laboratory in Washington, D.C., James Butler is taking this CVD process to the next level. They're growing not single stones, but wafer-thin diamond sheets.
One of the materials we grow starts with a non-diamond material, for example, a silicon wafer, onto which we put a very thin layer of these little diamond seeds. Think about shaking salt onto the kitchen table and having a whole bunch of salt crystals there. And then we put them in the CVD environment and they will grow. And as they grow together, they bump into each other and they become this mass. So it's all diamond, but with many different grains of different orientations.
Each diamond crystal bonds to another to form a mesh of crystals across the wafer, less than 0.5 millimeter thick. They can be made up to 20 centimeters wide. The shape of the template determines the shape of the diamond sheet. Perfect for making a wafer to replace silicon. They're much tougher than natural diamonds. They conduct electricity and resist extreme heat. These are true super diamonds. A simple test shows why diamonds make great microchips: the ability to conduct heat.
If I take an ice cube and a large plate of diamond, this diamond plate is going to transfer the heat from my hand through the diamond to the ice cube. And as you see, this just cuts, not really pushing. As the heat gets transferred through the diamond, it cuts straight through the ice cube.
And this is more than just a clever trick. Super diamonds have been filmed with image intensifiers that show how much more efficient diamonds are at conducting heat than the copper traditionally used in electronic components. The left plate is made of synthetic diamond, on the right, copper. These two plates are placed in ice and attached to a thermal image intensifier, which records heat as it travels through an object. As the diamond plate on the left shows, it conducts heat faster than copper, up to 5 times faster. It's this quality that makes the super diamond special. Scientists are excited. For the first time, they have a material that could challenge the domination of silicon. Microchips made from diamond wafers can run electronic devices at higher speeds and with more power without overheating. Faster, smaller, and more efficient. Razor-thin computers, long-lasting cell phones, and picture-perfect TV screens. Electronics are only the beginning. Today, scientists can make diamonds in shapes and sizes for uses that could revolutionize tomorrow. Researchers at the Carnegie Institution in Washington are trying to solve some of science's biggest mysteries. From how compressed gas can conduct electricity to how microscopic life can survive in extreme conditions. These investigations need extremely high pressures, which they create using a powerful vice called a diamond anvil cell. It squeezes an object between two diamond tips, creating a tiny environment of high pressure between them. It can recreate forces as extreme as pressure in the center of the Earth. For the Carnegie team's experiments, this wasn't extreme enough. But when they pushed the pressure higher, they hit a snag. The diamonds shattered. Russ Hemley, director of the Geophysical Lab, decided to upgrade the anvil by making an ultra-hard superdiamond.
Well, our group has been very interested in using diamond for high-pressure experiments for many, many years. And we basically needed to take this to the next level. We needed better diamond, stronger diamond, larger diamond than could be provided by Mother Earth or from conventional processes.
To create his super diamond, Hemley used a version of the CVD method to speed up the growth rate. The team then exposed the crystals to a high-pressure, high-temperature treatment to harden them further. The result? Another leap forward for super diamonds. The diamond not only grew many times faster, it also grew larger, 15 carats. In just 6 days, they'd created a stone 1/3 the size and 50% stronger than the Hope Diamond, a gem that took nature billions of years to forge. The new super diamond was so tough, it broke Hemley's hardness gauge. When used in the diamond anvil, this new super diamond proved the breakthrough he needed.
This can produce pressures that are millions of times the pressures found at the surface of our planet.
Now he can simulate forces so extreme they've never been studied before. Like those deep in the Earth's mantle, where pressures reach up to 1,300 kilobars. That's nearly 20 million pounds per square inch. This improved instrument lets Hemley study some of our biggest questions, like is there life in outer space? Hemley's team take 2 common strains of bacteria, including E. coli. They place them in a liquid and crank up the super diamond anvil. The liquid turns into a dense form of ice. Under the intense pressure, most of the bacteria are destroyed. But incredibly, 1% survive. If bacteria can survive these harsh conditions, maybe life exists in outer space, perhaps on other planets. The innovative uses for super diamonds extend beyond the search for extraterrestrial life. From super-sensitive electronic sensors to ultra-tough medical implants like synthetic joints. Thanks to super diamonds created under low pressure, diamonds will reshape the future. Super diamonds will change communications everywhere, especially on the battlefield. In constant use and battered by the elements, equipment like radios often break down in the harsh conditions of combat. But imagine if they were made of super diamonds. Already they can be shaped into tiny sound transmitters called nanoresonators, making vital radios and computers more robust and efficient. They can vibrate up to 100 billion times per second to create the highest quality sound yet achieved. But they're as tough as nails. All this from a diamond 1,000 times smaller than the width of a human hair. It's not just soldiers who'll benefit. Diamond resonators will eventually be used in everyday devices like mobile phones, allowing longer talk time and crystal clear reception. The same sparkle that attracts us to diamond jewelry reveals another of its secrets, its clarity.
It's transparent to light. It slows down light that passes through it.
As light enters a diamond, the dense carbon structure slows it down to less than half its normal speed. As it reflects inside the stone, the light appears to hang around longer.
You can actually force light to completely internally reflect and come out at some other angle. That's why diamonds look radiant, because light comes in from one direction, comes out another. It makes you think it's generating its own light, but it's not. All it did was redistribute the light coming in from other angles. It's remarkable.
Now you know why diamonds sparkle. The unique optical clarity of diamond, the perfect material for high-tech optical uses. A diamond is transparent across a huge spectrum of light, from ultraviolet to infrared. It's the only substance through which light passes virtually unaltered. From super diamonds, NASA can make super hard, super clear windows. The possibilities for super diamonds are endless. Soon you may find diamonds everywhere, from your workspace even to outer space.
The future of diamond, we're just seeing the very beginning of it, and I mean the stars are the limit when it comes to what we're going to be able to do with diamond in the future.
Nature took billions of years to perfect the diamond. Now we make super diamonds in days. Tougher, bigger, and better. The future is around the corner. Techniques to make diamonds are improving, and costs are falling.
Perhaps the day will come where diamonds are just as common as rocks in the street.
Like steel, plastic, or silicon, synthetic diamonds could revolutionize life. Welcome to the age of the super diamond.